Hi, welcome to this tutorial series on graph basics. In this video, we will see how the tables are converted into graph data. Tables are a very good breakthrough point for understanding graph modeling. Based on the given tables, graph modeling defines each table structure as a node schema or an edge schema, and uses data fields from tables as properties. When the graph modeling is done, all the table records are converted into nodes and edges. Then you need a properly designed graph visualization tool like Ultipa Manager to help you visually see the graph. The only thing that might need some effort is when some data fields need to be abstracted as nodes, in order to highlight the feature of records in a topological way. Converting tables into graph is a procedure both intuitive and technical. Now let's practice. These are tables of a course enrollment scenario. From the records, we learned that Jason is a student majored in computer science, and graph theory is a course offered by Jason's department. As we know, Jason and graph theory are nouns that represent entities, so we define them as node. The third table refers to some information from the first two tables, which tells Jason enrolled on graph theory. This is an action expressed with a verb, so we define it as edge and point it from the initiator of the action to the recipient. Let's analyze all the records in the same way. Green nodes represent students, blue nodes represent courses. Edges point from students to courses they enroll on. All the records turn into a graph like this. This is an approach by common sense to decide if the records in the table are nodes or edges, which is define nouns or names as nodes, define verbs or actions as edges. But common sense doesn't work all the time. We need a technical approach, which is analyzing the data fields. A data field that refers to another table from its table is called foreign key. In the enrollment table, the student ID and the course ID are both foreign keys. If a table has two foreign keys that refer to other tables, then the table is edge. If the table has no foreign key, then the table is node. You may ask, this technical approach doesn't cover all the cases. What if the table has one foreign key, or has three foreign keys, or even more? In fact, the data field department in the student table and the course table is more commonly recorded as a table rather than a data field, which is understandable since the departments usually have plenty of information to record. At the same time, these two data fields become foreign keys that refer to the department table. Let's reanalyze these tables. The department table has no foreign key, so department is node. And the student table and course table each has one foreign key pointing to the department table, so define these two foreign keys as edges that point from the student and courses to department. This technical approach now covers the cases where the number of foreign keys in a table is less than 3. Let's practice using another example. These are tables of a Bankcard transaction scenario. The client table has no foreign key, so client is node. The card table has one foreign key referring to the client table, so card is node. And there's edge pointing from client to card. The transaction table has two foreign keys, both referring to the card table, so transaction is edge pointing between cards. Here's what the records look like in a graph. Now let's explore this scenario a little bit. There's a data field device in the transaction table. It records on which device the transaction was initiated. If a transaction is suspicious, then other transactions on the same device may deserve our attention, since they are probably initiated by the same person for a similar purpose. This is an application scenario in the category of real-time decision-making. The best practice to realize it on a graph is to create node for each device. In other words, to abstract device as a table and turn the data field into a foreign key. Now it seems that we should define this foreign key as edge and point it from transactions to devices. But this is technically illegal in an Ultipa graph system, because we already defined a transaction as edge. An edge cannot initiate another edge. So let's define the transaction as node and define all the foreign keys in transaction table as edge. Let's polish our technical approach. Define a table as edge only if it has double foreign key. In other cases where a table is defined as node, each foreign key of the table is an edge. But be careful when you see a double foreign key in a table, like in this scenario of foreign posting, where a user writes a post either to reply to another post or to start its thread. If you analyze the post table, you will see two foreign keys, but you just cannot define the post table as edge, because the second foreign key refers to the post table itself, and this decides that the post needs to be node. Let's review what we've learned so far about converting tables to graph. Basically, any table can be defined as a node schema. For each foreign key that appears in a table, define an edge schema between the node of this table and the node of the foreign table. If a table has only two foreign keys and neither of them refers to the table itself, simplify this table as an edge schema between the two foreign tables. In case there's need to abstract any data field as node, define the table and the data field as two node schemas, and define an edge schema between them. And make sure that you assess the pros and cons before abstracting data fields as nodes. Abstracting data fields as nodes refines the topological structure of the graph. And a good topological structure facilitates graph query. But be aware that the total number of nodes and edges in the final graph certainly increases after abstracting data fields as nodes. A meaningless abstraction might lead to irrational supernodes that hinder the proper usage of graph query. For example, it is a bad practice to abstract the gender of a user table as nodes, as it definitely creates two supernodes, the male and the female. This is the summary of this lesson, and please follow our lessons in the future. We will show you more about Ultipa graph system and graph query.